Hey everyone. In this video, we're going to be looking at the functional groups of organic molecules. Now, in the last set of videos, we looked at the hydrocarbons, everything here in the top row, alkanes, alkenes, alkynes, and the aromatic groups. And in this set of videos, we're going to start looking at functional groups that have atoms other than carbon and hydrogen. And so an amine is any functional group that has a nitrogen connected to carbon. An alcohol is an OH. An ether is an oxygen between two carbons. A thiol is a sulfur and a hydrogen. An aldehyde is a carbon double bonded to an oxygen next to a hydrogen. A ketone is a carbon double bonded to an oxygen sandwiched between two carbons. An ester is a carbon double bonded to oxygen with an oxygen and then another carbon. A carboxylic acid is a carbon double bonded to oxygen with another OH, and an amide is a carbon double bonded to oxygen with a nitrogen. So I would highly recommend memorizing these as soon as you can. Being able to identify these functional groups is the first step to being able to predict their reactions or to name them. So being able to identify the type of functional group from a structure is going to be the first step to everything. So definitely memorize these. Let's do a quick study check. Here's a drug used to treat high blood pressure. Can we identify all of the functional groups in this molecule? Well, if we look at it, I think the easiest thing to see here is a giant phenyl ring. So that's an aromatic functional group. Well, right here, I see that we have an OH. And so that's going to be an alcohol. And what did we call it when we had a nitrogen connected to carbons? That was the amine. And what about when you had the carbon double bonded to oxygen next to a nitrogen? Well, that was the amide. And the last one here is just an oxygen sandwiched between two carbons. And that's what we called an ether. And so those are all the functional groups in this molecule. So for the rest of this video, we're going to be focused mostly on alcohols. So alcohols contain an OH group, also known as a hydroxyl group. But you can call it an alcohol or a hydroxyl. It means the same thing. And we can classify alcohols based on the number of carbons connected to the carbon where the alcohol is attached. And so we can look at a carbon that has an alcohol attached here, highlighted in blue. And if he's connected to one other carbon, we would say that it's primary. We abbreviate that with a 1° sign. If the carbon where the alcohol is attached is connected to two other carbons, we would say it's secondary. And if the carbon where the alcohol attaches is bonded to three other carbons, then it's tertiary. Let's do a practice. Classify each of the alcohols in the following molecule. So let's figure out if these are primary, secondary, or tertiary. So this one here on the right, we want to look at the carbon where the OH is attached, right here. And it looks like he has one bond to another carbon, so that will be primary. This one in the middle, we want to look where the OH is attached. It's attached right there. And so how many other carbons are connected here? Well, I see one bond to a carbon and another bond to a carbon. So that would be a secondary alcohol. And over here, the OH is attached to this position. And that carbon has 1, 2, 3 bonds to other carbons. And so that would be a tertiary. Next thing we're going to take a look at is naming alcohols. Excuse me. And so naming alcohols follows the same IUPAC system that we learned for alkanes, except we're going to replace the E ending with OL. And then we're going to assign a number where the OH attaches to the parent chain. So this molecule here on the left has 5 carbons. And so in chapter 11, we learned that the prefix for 5 was pent. And then we add the suffix ane because it's an alkane. It's just a hydrocarbon. Well, this one on the right also has 5 carbons. So it's also pent, but instead of pentane, we're going to take off the E and we're going to add OL because there's an alcohol. So the OL indicates that there's an alcohol. But we need to specify which carbon that alcohol is attached to. And so it's attached to carbon 1, and that's where the 1 comes from. So name it like an alkane, but change the E to OL and add a number. All right, let's practice naming these. So this one here on the top left has 3 carbons in the parent chain. And so we would name that propane if it was an alkane, but we're going to drop the E. We're going to add OL, so propanol. And the OH is attached to carbon number 1. So this is 1-propanol. The one here on the top right also has 3 carbons in the chain. So it should also be propanol. The difference, the OH is attached to carbon 2. So this one is 2-propanol. Now the one here on the bottom, I'm going to number it from right to left to make sure the OH gets the lowest number possible. I see 6 carbons in a row. And so I would name this hexane. We're going to drop the E, turn it into an OL because there's an alcohol. So hexanol. And it looks like the alcohol is attached to carbon 2. So 2-hexanol. And then right here on carbon 4, it looks like there's a methyl group. And so this is going to be 4-methyl 2-hexanol. So number the parent chain, name it like you would an alkane, but turn the E into an OL, and then give a number where the alcohol attaches. And if there's any other substituents, they go at the front of the molecule. All right, let's practice going the other way around. If I give you the name, can you draw the structure? So cyclohexanol. So hex tells us that there's 6 carbons, and cyclo tells us that it's in a ring. So 6 carbons in a ring, and we have to have an alcohol somewhere. Doesn't matter which carbon you put it on, because it's the same thing as just drawing the molecule rotated. All right, so the next one. Looks like the parent is bute. Bute means 4. So we know we're going to have 4 carbons. So 1, 2, 3, 4. I'm going to number it. And it looks like the alcohol is attached at carbon 2. And then there's supposed to be a methyl group also coming off of carbon 2. So there we have it. 2-methyl, 2-butanol. Okay, so now that we talked about how to name alcohols and classify them, let's talk about some of their physical properties. One of the most important things about alcohols is that they mix with water. Now let's take a look at why. Water is a polar molecule. Oxygen is more electronegative than hydrogen. And so you form a dipole going towards oxygen and away from hydrogen. The oxygen is partially negative. The hydrogen is partially positive. Now, if you have an alcohol molecule here, it has a similar dipole. That OH bond is very polar, and so you end up with the partial negative and the partial positive side. Well, that partial negative wants to line up to the partial positive of the nearby water. It's an electronic attraction. Opposite charges, kind of like magnets, they stick together. And so this is what we call a hydrogen bond. It's a type of dipole-dipole interaction, but it's extra strong because oxygen is super electronegative. So it's an extremely strong type of dipole-dipole, and we call it a hydrogen bond. And because alcohols have the OH group and waters have an OH group, they can hydrogen bond together, and they tend to mix well. That's why you can have something like vodka, which is 40% alcohol and 60% water, but they completely mix. This is because they're hydrogen bonding together. Now, it becomes a problem when there are a lot of carbons in your alcohol molecule. So hydrocarbons are nonpolar. They can't hydrogen bond. And so if we had something like this big molecule down here, the tail, if you will, is nonpolar and repels water because it can't hydrogen bond. So even though you have the OH that wants to dissolve in water, the tail stops it. And so I use the analogy of flotation devices for this, right? If you have an OH group, it wants to swim in the water like a kid wants to get in the water. But the carbons are like floaties. And so if you have too many carbons on your molecule, it can't get in the water because the hydrocarbons keep it afloat. So silly analogy, but pretty accurate. Few carbons on your molecule, the OH allows it to go into the water. Too many carbons, and it can't get into the water because the hydrocarbons don't want to mix with water. And the general trend is alcohols up to 3 or 4 carbons are soluble. And then beyond that, it's diminishing returns. So more solubility with fewer carbons. So less soluble with more carbons. And more soluble with fewer carbons. So if I give you a collection of molecules, can you tell me which one is most likely soluble in water? Well, it's probably going to be the one with the fewest number of carbons. And so that's easily identifiable here because this one only has 3 carbons. All the others have a lot more than that, and so they're going to be less soluble, right? Fewer carbons, more solubility. More carbons float away from the water. All right, so that's it for this video. Thanks for watching, and I will see you in the next one.